Physics 1 lab, constant velocity. Introduction. So, what is the purpose? The purpose of this lab is to demonstrate one-dimensional motion in the real world of physical objects moving with constant speed, and then comparing it to computational models. Key principles is Newton's second law and Newton's first law. Newton's second law is that acceleration of an object is directly proportional to the net force acting upon it, F net, and inversely proportional to the object's mass. The first law, Newton's first law, states that an object at rest stays at rest, and an object in motion will stay in motion uh, with the same speed unless an unbalanced force is applied to the object. So, relevant formulas is going to be Newton's second law, where F is equal to ma, which is force is equal to mass times acceleration. Um, since our object is moving with a constant velocity, we can ascertain that the acceleration is going to be zero. Um, we can derive this from our other formulas where using the position update formula and the velocity update formula. Um, Not necessarily thanks to code, but these equations are what allow us to calculate and simulate or our expected positions and marked by hand. So reasoning. The simplest way to represent a object's position is denoted by its position and its time, or at some time. So position versus time. Uh, it's the most visually appealing way of achieving position versus time is graphing it, such as the example one we have up here. So in our case, we had a dry erase marker that we pushed across a meter stick. And so our initial conditions, the initial conditions is that the position was 0, negative 0.00159 in the y direction and 0. The F net is going to be 0, 0, 0, and the time is going to be 0 seconds. Our computational model, we have the initial position as 0, comma 0.1271750 and initial velocity as in 0.53. The mass is 1, time is equal to 0, change in time is equal to 0.33 seconds. So we got that from the change in time that we experienced whenever we use tracker on our, so the T right here. As you can tell, you only are going to see positions in the, change in the Y, because that's the only direction that we're changing. We're not changing our X. So in the experiment, the marker is filmed being pushed in a straight line to mimic constant force. Tracker is then applied to obtain its position versus time value. The values are then plotted on a graph for analysis. The coding, we input calculated values into glow script. We use loops to calculate until time is reached, updating its position. Programming outputs position versus time graph of the produced values. And then we can compare simulated estimates to actual evaluated estimates. So our comparison came to this, actually shows minor similarities to simulation following the same relative path. Um, it's more significant that as time continues, the actual position of our marker doesn't correlate with our simulated position, mostly because we have not ideal um, forces acting upon our marker in the real world. We have things such as friction, air resistance, and stuff like that. But as you can tell, even these minor things acting on our marker will decrease it over time, over a substantial amount of time. So the chief component of error will lie in the fact that our experiment cannot be, done in conditions that are present in the simulation. We can't have ideal conditions from simulation to real world. There is a possibility for human error, even with numbers handling our data or collection. We might have went wrong. Perhaps we even pushed the marker itself in the wrong way, or the camera was held improperly. Discuss some questions. What if flip the axis of consideration? What do little more than change the signs of the results? The numbers, magnitude would stay the same. What does it mean? No, they are many contributions of force that could result in F net of zero or net